All right, senior math, welcome back. Today we are continuing with our hypothesis testing, and we are going to look at hypothesis testing with two means today when you have two populations. So many scientists often try to compare more effective or more efficient ways of doing things, but it's often hard to tell whether their new experimental method is better or not. So it's one thing to be able to say, okay, I think this method is better. It's another way to be able to prove that the method is better. We often need to compare two different means to see if there is a difference between the two methods. The mean of the original method and the mean of the new, more effective method. So one way of being able to tell whether the method is more effective is look at the means of both of those methods. Which one is lower? Which one has a smaller standard deviation? And we can use that data to then help us determine statistically whether or not we have enough information. So, for example, the U.S. Postal Service is interested in reducing its massive 350 million gallon per year gasoline bill by replacing gasoline-powered trucks with electric-powered trucks. To determine whether significant savings in operation costs are achieved by changing the electric trucks, a pilot study should be done using 100 gasoline trucks and 100 electric trucks under similar conditions. If the electric trucks have more or have a mean cost that is cheaper than the gasoline trucks, then it should appear that they are better. But how can we tell if this sample is a good measure of all of the gasoline and electric trucks used? So it makes sense to test both trucks and see which one has a lower mean. Do the electric trucks cost less? Do the gasoline trucks cost less? But how can we tell whether those 100 trucks is a good representation of the entire population of all electric trucks to use and all gasoline trucks to use? So we can use our sample mean, assuming we have a large enough sample, assuming you have roughly larger than 30-ish, it should be a good enough, it should be roughly a good estimation for the entire population. And we can test this using a hypothesis test to determine which of those means, or if there's enough data, or if the data suggests enough evidence to support that is significantly or statistically significant to show that one mean is better than another. And we're going to do this using the exact same processes, the hypothesis testing that we were practicing last week. All right, so when we're doing a hypothesis test between two means with two populations, our formula changes a little bit. Typically, we had z equals x1 minus the mean, or we had x minus the mean divided by the standard deviation divided by the square root of n. Well, now that we have two means or two populations, our standard deviations change, or our z-score is changing a little bit. So anytime I see a 1, so I have these like x sub 1, sigma sub 1, n sub 1, that always represents from the first population, so from one of the groups. So x is going to be, x equals the mean from that first population. Sigma equals the standard deviation. Sorry. The standard deviation from that first population. And then n equals the sample size, the number of tests, or the number of people in that population that were tested. And so it just determines whether it's coming from this first the first population and the second population. Is that sigma 1 or sigma 2 or n1 or n2? We will still be doing the same number or the same types of tests: a left tail test, right tail test, two tail test. We're doing all of those same things. But what these tests are comparing is the difference in the means. So difference, once again, means subtraction. So if there is no difference in the mean, then one mean minus the other mean should equal 0. So if there's no difference, if the means are the same, then mean 1 minus mean 2 would equal 0. So if you're trying to show that there is a difference, and then your alternative hypothesis would be h sub a would equal mean 1 minus mean 2 would not be equal to 0. If you're trying to show that there's a difference, if you're trying to show a difference between the means, then that means that the first mean minus the second mean would have something other than 0, something that's not 0. Well, if you're trying to show that one mean is greater than another, or if it's believed that one mean is greater than another, you'll have your right tail or your left tail test. So if you think that, oh, I didn't flip-flop these. This one should be like this. Sorry. So if you want to show that one mean is larger than the other or smaller than the other, you could do that left tail test or that right tail test to determine those means to show if there's significant data. Typically, we do two-tailed tests on these, but there are a few times when left and right-tailed testing does come up. And once again, your alternative hypothesis is just going to be the opposite of what shows up. So if you have less than, then greater than is going to be your alternative hypothesis. If you have greater than, then less than is going to be your alternative hypothesis. The steps, once again, are pretty much the exact same thing as our hypothesis test we were doing last week. State the null and alternative hypothesis. Once again, that's always your first step. Determine the type of test, whether it's a left-tailed test, right-tailed test, to figure out those critical regions. Plug in the information into your formula. Once again, your formula is right here. It looks a little bit different, but it's still pretty much standard, same thing. Determine whether z-score falls within that critical region, and then keep or reject the null hypothesis based off of whether the z-score falls in the critical region or not. So let's do an example. Sorry, I apologize. All right, example. So to determine whether a car ownership affects the student's academic achievement, 2 random samples of 100 students were drawn from a school's student body. The grade point average for n equals, or n sub 1 equals 100 non-car owners. So we have n sub 1 is 100 non-car owners, was x sub 1 is 2.70. So the grade point average of the non-car owners was 2.70 with a standard deviation of 0.36. Well, n sub 2 was 100 car owning students that had a grade point average of standard deviation of 2.54 and a standard deviation of 0.40. So does this data present sufficient evidence to indicate the difference in the mean achievements between car owners and non-car owners? So is there enough information to show that there is a difference in the means? So because we're just trying to show a difference, in the mean between car owners and non-car owners, starting off with our, I'll move this up here. Starting off with our hypotheses, our null hypothesis is that there is no difference. Is that mean 1 minus mean 2 is 0. So there's not a difference. That's our null hypothesis, just the general belief that owning a car shouldn't affect whether or not whether your academic achievement goes. But let's see if grade point average is affected by owning a car. So we're just trying to see if there is a difference. So our alternative hypothesis is that the difference between the two should be not equal to 0. There is some sort of difference between those two means. That's what we're hoping to find. So this is going to be a two-tailed test. So if we were to think about our normal curve for our two-tailed test, that means, because we always do 95% confidence, that we have our 2 critical regions. So this is negative 1.96 and positive 1.96. Are those the correct numbers? Let me check that really quick. For whatever reason, my mind's drawing a blank whether those are the correct numbers we want for our critical region. Positive 1.96 puts us at 0.97500. Yeah, okay, so that should give us 2.5% on each side. So if we get a number that is greater than 1.96 or less than negative 1.96, then there is enough information to show that we will reject our null hypothesis and keep the alternative hypothesis, showing there is a difference between the means. But if we don't reach 1.96 or negative 1.96, then out of 95% confidence, we are 95% confident that there is not a difference between, or there's not enough significant evidence between the data to show that there is a difference between the means. So let's then figure out if we fall within this. So we need to use this formula right here. We're going to start plugging in some information. So let's figure out what the z is. So z is going to be equal to x1, which I know x1 is 2.70, minus x2, which we have x2 of 2.54, divided by the square root of sigma 1, which is 0.36, divided by n1, which is 100, plus sigma 2, which is 0.40, divided by n2, which is 100 again. And all I have to do is I have to just plug this into the calculator. So 2.7 minus 2.54 all divided by the square root of 0.36 over 100 plus 0.4 over 100, or 0.40 over 100, gives me 1.84. So 1.84 is pretty close to my critical region, but it doesn't quite fall within my critical region. It's just outside of the critical region. So the evidence suggests that there might be some sort of potential that car ownership might affect it, but this data, this specific evidence, does not suggest enough information or does not have enough data to prove that there is enough of a significant or statistical significance to show whether that car owning does affect your school achievement. So we are going to keep the null hypothesis because we did not fall within our critical region. And so pretty much everything we're doing today is pretty much the same stuff we were doing last week. The only thing difference is we have this new z-score formula. So the only difference is we have this new z-score formula for two populations. Other than that, everything else is the same. You just have a little bit more data thrown at you this time that you have to sort of organize. But highlighting some things and underlining some things is always helpful. Plugging it into that information and then putting it all in. And you can type this into Desmos. If you have trouble getting that started, let me know and I can help you type that into Desmos if you would like. But other than that, that's all we have for today. Let me know if you have any questions and have a great rest of your day.